I hope everybody was able to enjoy the long weekend. Okay. Now, so I got a few good questions about Chapter 2. So that means that's less that you'll have to do for Homework 2. I'm starting to get some questions about Homework 2. So based on those questions, if something needs to be clarified in the problem statement, I'll go ahead and edit the textbook to do that. So I won't change the substance of a question, but just, again, wording or maybe in the surrounding text. So I'll be sure to do that tonight based on questions I got today. Now, so I'm not going to be doing spending time on MATLAB things unless there are questions, specific questions that anybody here has about Homework 1, and that's the only thing I'll do related to that. It is time to move forward into Chapter 2. Still waiting to hear back on who will be my substitute when I'm gone next week, and hopefully I won't come back. I'll be in Germany for a Siam meeting, so hopefully I won't come back to find that Hurricane Irma destroyed everything. Okay. So, does anyone have any homework 1 questions at this point? Okay. Because, I mean, there are 21 of you in the class. Only 9 have turned it in. Please get it in. So, I mean, I do like to be fairly loose on deadlines within reason, but at some point it will no longer be within reason. So, because, again, we're moving forward. Come along. Or what you have no choice. I'm moving on. But yes, okay, what questions? 11? Yeah. Okay. Sorry, my mouse is not cooperating. Okay. Well, just because they're different things. Well, yeah, because now when x is a real vector, all right, so I'll go ahead and write this in here. So x transpose x, well, I'll make an assumption here. So assume x is in C3, so a three-dimensional complex vector. So x1, x2, x3. So then, actually, I'll have to edit that out of diary. I'm putting semicolons here. By making semicolons put in between, what kind of vector is this? What shape? Column vector. Yeah, with the semicolons, it's a column vector. And I need that, in this case, in order for x transpose x to be correct. So x transpose x, and in MATLAB, that would be x dot quote times x. So here's how it'd be written mathematically, with the up arrow meaning a superscript, and then this is how you would write it if you're doing it in MATLAB. So that would just be x1 squared plus x2 squared plus x3 squared, but x Hermitian transpose x, so superscript h, which would be x without the dot, transpose times x. That would be x1 squared plus, or absolute value of x1 squared plus value of x2 squared plus absolute value of x3 squared. Now, if x1, x2, x3 are real numbers, there is no difference. But there's a big difference when x1, x2, or x3 are complex. So so absolute value of x squared is x1 times conjugate, the complex conjugate of x1. Sorry, x. Well, hold on. I'm going to fill in some assumptions here. I mentioned this before when I did some fun facts about complex numbers. So absolute value of z squared is u squared plus v squared, always a real number, regardless of whether z itself has an imaginary part. But z squared is u plus iv, u plus iv. So if you work that out, that's going to be u squared minus v squared, because you have iv times iv. I squared is minus 1. And then you're going to have I times 2uv. So you take a complex number and square it, there's going to be an imaginary part. So it's a distinction between these two operations, squaring the number itself or squaring the absolute value, that leads to being able to get some unexpected results for to show you why when you compute this, you can get results that are not what you'd expect. Because you would expect this to be a magnitude, a non-negative real number, but now you can see that that's not always going to happen. So you have to come with 3 concrete examples that produce those 3 things. Right. Yeah. So find an x that makes it 0, find an x that makes it negative, find an x that makes it imaginary. Yeah. Because, I mean, there's still a well-defined function. You won't be able to have one x do all 3 at the same time. Okay. Other questions on homework 1? Okay. So the 12 of you who have not gotten in yet are intending to soon? Please? Okay. All right. So I just want to make sure. Okay. And I mean, if it's because you are struggling at certain ones, if you don't feel like asking about them here, that's fine. But please do outside the class. If it's a matter of being stuck. Okay. Now, chapter 2, there's just a couple sections in it, which I'm going to spend time on this week. The substitute, whoever it is, next week, will start getting into the next chapter, chapter 6, which there won't be homework doing that for quite some time, but that's also a long chapter. So we're still really we haven't done real numerical analysis yet. There's still a lot of preliminaries. First, getting up to speed with MATLAB, and second, understanding basics of error analysis, floating point arithmetic, which is what I'm going to talk about on Thursday. And then after that, when we get into chapter 6, we start looking at, okay, here's some actual mathematical problems, and how do we solve them numerically? How do we design methods to do that? So we're still in the setup stage, but because this is a more advanced course, there's more setup required. Now, so what I'm going to do is, like I said last week, what I expect you guys to do, and I know at least some of you have, is get into reading chapter 2, certainly section 2.1. And if you haven't done that yet, then I urge you to at least between this class and Thursday. So what I'm going to do is I'm not going to go through the whole section here. What I will do is some examples that are meant to illustrate all the points, the main points of this section, so that if you haven't read it yet, or even if you have, if you go back and look at it later, hopefully what I've done here will today will reinforce these things. Okay. And so I'll carry this out here in MATLAB. Okay. So what I'm going to focus on is some examples: absolute error, or absolute and relative error, and also forward and backward error, and also conditioning. Okay. Now, we also need, since I'm typing this here in a MATLAB diary, just so there's no issue with having to read my penmanship, I'm going to have to lay down some notation here. Okay, so first, all right. So, if I flip to the textbook here, and the notation that I use here. Yes? Yes?
Is there something rubbing against the microphone? We're getting a lot of feedback here.
Good question, since I'm not sure where the microphone actually is. Oh, is that right there? Yeah. Ooh.
Did the paper get turned to where the AC is blowing on it again? That's probably what it is.
So like the AC needs to be turned down or something, or?
Even if you turn it down, it will still hit the mic unless you can turn the paper again to where it's not hitting it. That's what
Turn to what? Oh, that. Okay.
It's the paper rubbing it.
Oh, I see. But the paper still needs to be there?
Because it blocks the air.
I see. Oh, okay. So this is like a mitigating thing, but it's not. So either you're dealing with the air going against it or the paper rubbing. So either way, I guess. Okay. All right. This is a problem. Okay. I'm not sure if I can safely mess with this though. Let me check the thermostats in my office. One of them supposedly controls what happens in this room. Because I don't know if there's any sort of volume control that I could adjust for what. Because I'm also coming through too loud, or?
No, the volume level's fine. The feedback has actually subsided substantially. So I don't know if you did anything.
The only thing I did was I just adjusted the thermostats in my office, so hopefully it wouldn't blow in here as much. Okay, we'll see what happens. All right. Now, so when we're computing approximations and we're trying to understand how the error behaves, and this is a summary of what's happening in what's described in the textbook. We're computing y equals some function of x. X is our input. Okay, I'll just write this down here. X is whatever our input is. Y is our output, and therefore like solution. If you can think of as algorithm to produce y. I mean, you can think of it as an ordinary function, and that's what we're doing in some of the examples that I have. But it's meant more broadly than that. It's not your typical garden variety y equals f of x that you get in your garden variety math course, because this is anything but. Okay. The types of error, if I were to summarize them as briefly as possible. We have data error, which is the error in x. For example, maybe x is obtained by some sort of measurement. So that would be an example of data error. Or maybe x comes as a result of some previous computation, which is going to have some error in it as well.
So would the value of pi in MATLAB be like a data error if you couldn't really, because the precision?
Yeah, you could think of that. Yeah, just because pi can't be represented exactly. Yes. So yeah, if you think if you're using pi as input, part of your input into some formula, yes. On the other hand, we have computational error, of which there are many kinds, but we have that'd be error in y, which could be due to computer arithmetic, truncation of approximation, and I'll get into more of these as we go. For example, if you're representing a function by a Taylor series, you have to cut it off at some point. If your solution y is produced by an iteration, you have to stop the iteration at some point. You can't let it run forever. Those kind of things are examples of truncation error. Okay, so, and the thing is, all right. So what we really care about is, well, the error in y. Because that's what, how accurate is whatever it is we're trying to compute, and I refer to that as forward error. But what's often more practical to estimate is the error in x, and that's referred to backward error. So if we want forward error, but backward error is what we might be able to more readily estimate, that's where the importance of the condition number, that is where the condition number comes into play. And the relationship between them is very simple, that forward error, what we want, is equal to backward error, what we care about, times condition number. And this applies whether we're talking about absolute errors in condition numbers or relative errors in condition numbers. So that's why I left them out of this last statement, because as long as you're consistent, as long as you're dealing, have everything absolute or everything relative, then this equation I have here applies. Now, so f of x, that is the exact solution to whatever problem it is we're trying to solve. Maybe we're just trying to compute maybe all we're trying to compute is the value of a certain function. Maybe we're trying to find a root of an equation. Maybe we're trying to evaluate integral. All of these problems I'm making very abstract, that we're trying to compute some y from some input x using some algorithm f. So like in a textbook, we have that representing the exact solution. Now, to refer to approximations, if I remind you of how that's done in the book, okay, I use hats to refer to approximations. So, for example, right here, I have f of x hat. So the hat refers to approximate input. And then, so for instance, that could be applied to the input. It could apply to the output. It could apply to the algorithm. Any of these things can be approximated. The trouble is it's a little cumbersome. I can use up arrows in MATLAB, but I'm going to just set a notation for what I'm typing into the diary. So I'll just state that up front. Okay. So YH, so that would be my abbreviation for y hat, is the approximate solution. And similarly, FH is f hat, xh equals x hat, and so on. So if I put an h after a variable, that refers to the hat. That means it's an approximation. Okay, just for what I'm going to lay out here. Okay, so my first example is just computing the exponential function at a given x. Okay. Now, I'm going to specify a specific x. Okay, that sounded awfully redundant. I'm going to specify x. X is equal to 10.1. So that's the value I want to plug into the exponential. Now, computers cannot evaluate the exponential function exactly. Not just because there's a computer arithmetic, but because really the only function that a computer can evaluate exactly is a polynomial. Because for a polynomial, well, also certain rational functions, because you can perform, because they involve the basic operations: add, subtract, multiply, divide. Anything beyond that, exponential, sine and cosine, square roots, those cannot be evaluated exactly. There's going to be some error beyond the error you get in arithmetic. So this is my exact x. So my exact y, just for the purpose of studying error, we'll just go ahead and plug that into MATLAB's exponential function. So this, to high accuracy anyway, is our exact value. Now, how are we going to approximate our function? F of x is the exponential. So this is our exact algorithm. I'm going to approximate the exponential by its second degree Taylor polynomial centered at 0. So that'd be 1 plus x plus 1/2 x squared. By the way, who knows from Cal 3, when you have a Taylor expansion centered at 0, what do we call that? Maclaurin expansion. Okay. All right. So now the thing is, these kind of approximations tend to be accurate only near the center, and we're not near the center. X is 10.1. So, and I know 10.1 seems like an odd choice, but it'll make sense later. I promise. Okay. So now I'm going to go ahead and compute my approximation YH. That'd be 1 plus x plus 1/2 times x squared. So you can see, compared to the exact value, it's a bit off. Okay. So now I'm going to compute my forward error. I should say absolute forward error. Okay. So I'll just name that as a variable. And that's just going to be YH minus Y, based on the definition in the text. So it's pretty bad. And we can also do the relative forward error. So that would just be the absolute error divided by the exact value. So when the now relative error, you can think of it as a percentage error, and you don't want that. So if I take this and multiply it by 100, so the percentage error is minus 99.7%. You're that far off. You might as well use 0 for an approximation in that case. You'd be pretty much just as accurate. Okay, so those are the forward errors that we get from our output. But I want to compare forward errors to backward errors so we can see what the condition number is. Because what I want to highlight here is this a well-conditioned or ill-conditioned problem, a problem of computing the exponential? So what I'm going to do is, with backward error, what we do is we assume that the approximate output, which is defined to be the approximate algorithm applied to the exact input, x, is also equal to the exact solution of a nearby problem. And when I say nearby problem, I mean the input is changed. So you have, instead of computing the approximate exponential, this Taylor polynomial applied to the true x of 10.1, we could think of our approximation here as the exact exponential of an erroneous x. So, in other words, yh is the exponential of some erroneous xh, which is our x hat. So, how can I get x hat in this case? How can I solve for it, given what we have right above? If this applies, how do I get xh? Natural log. Yeah, so natural log of yh. Okay, well, again, it's a bit off. So it's so our very bad approximation is the exact solution of a problem that's in no reasonable sense nearby, because our true x is 10.1. Here we get this approximation by taking the exact exponential of 4.12. Yeesh. But now we can compute backward error. So absolute backward error, and this is how I'll abbreviate it. So that would be the x hat minus x. Okay, and then relative backward error, that would be the absolute backward error divided by the exact value of exact x. Okay. So now that we have forward and backward errors, both absolute and relative, we can determine condition numbers. So the absolute condition number, that would be the absolute forward error divided by the absolute backward error. Okay, and that's kind of big. And the relative condition number is the relative forward error divided by the relative backward error. Not quite as bad, but so this is an indication of how much absolute or relative errors in the input are magnified in terms of to produce the forward error. So this is one thing to keep in mind, is that just because your input error is small, it doesn't mean your output error is going to be small as well. Because if a problem is badly conditioned, if you have a large condition number, we're going to see some amplification. Sometimes you can get lucky and have a very well-conditioned problem. Maybe your error is actually reduced. But generally, that's not what happens, unfortunately. Okay. Now, for if you look at condition number analytically, so what we have is, for the absolute case, we have the, I use absolute values for everything. So exponential at your x hat, actually, I'll do it this way. YH minus y, that's the same as e to the xh minus exp to the y. But by the mean value theorem, that's equal to the exponential at some value c between, whoops, that should be an x, between xh and x times the difference in between the x values. If you don't remember the mean value theorem, that was covered in Cal 1. I suggest you look that up in the appendix A, where all the where the calculus review is. So a difference in y values is equal to the derivative at some unknown point times the difference in the x values. That's something that's useful quite often, actually, especially in this field. So it's the derivative well, of course, the exponential is its own derivative. So what we have here is the absolute condition number is this is actually the exponential of roughly 8 or so. So I mean, because we don't know what this value is, but so we can see because it's related to the exponential why the absolute condition number is quite large. On the other hand, relative condition number, and this is worked out in the text, is equal to the general formula is x f prime of x over f of x. Well, if you plug in f being the exponential, it's its own derivative. So we just get the absolute value of x. So that's why the relative condition number isn't quite so large in this case. Okay. So so we get an idea from examples like this if we are able to, based on our assumption about backward error, that's the exact solution of a perturbed problem, we get an idea as to what the condition number is, and so we can get a feel for, is a problem ill-conditioned or not. Now, if I change the example a little bit, change how I compute YH. So instead of using the second degree Maclaurin polynomial, I'm going to use a Taylor expansion with a different center. I'm going to center it around 10. This is why I used 10.1 earlier. So if I work out the Taylor series at the center equal to 10, this is what I get. So this is the second degree Taylor polynomial at the center. I'll call the center x naught is equal to 10. So since my value of x at 10.1 is near the center in this case, I should have a much more accurate approximation. So now I can try that. So my new approximation is going to be e to the 10th times 1 plus x minus 10 plus 1/2 times x minus 10 squared. Okay, and if I compare this to the exact value, much closer, much better. So now we can get the absolute error again. All right, so I mean, these are large numbers, so having this forward error is actually not bad. The relative forward error is now really small. Remember, this is a percentage. So that shows that this is a very good approximation. And then if I do the same thing as before and figure out backward error, so my approximation is the exact solution of a nearby problem where the perturbed x really is near because it's very close to 10.1. So that's good. So now I can compute the backward errors. That are both quite small. And then I can compute condition numbers. Again, so if I have the absolute condition number, and then the relative condition number. All right, now, what do we notice about the absolute condition number this time? Compared to before, I'll scroll up. Here's what it was before versus now. What? Yeah, and it wasn't exactly small the first time. It's still quite big. And also here, it's this relative condition number also larger than before. Now, and actually, these are much more in line with the analytical formulas for a condition number. But this is close to x, and then this is close to e to the x. So the reason why I make this point is the condition number is independent of the approximation. It's in other words, property of f, nothing to do with f hat. That's the important thing. Is that we're going to have certain problems that we'll look at, whether it's in this course or the next course, 461, where we might throw different methods at it. But if a problem is ill-conditioned, all of those methods are going to have problems. And it's really a tough nut to crack in these cases. So a condition number is a property of the underlying problem you're trying to solve. Whereas whatever algorithm you choose, we can have a stable or unstable algorithm. So if both properties are good, if you have a well-conditioned problem, stable algorithm, you can expect an accurate answer. If both those things don't hold, you could still get an accurate answer, but it's a bit more of a crapshoot in that case. All right, so now I went through this example because you're going to be doing the same kind of things in some of the explorations to figure out backward error and then therefore condition numbers. So any questions about the process in this case? Okay. So now I'm going to look at a different sort of problem. So I'll just put a little divider in here. So suppose you're given a function f of t, and the problem you're trying to solve is compute the integral of f on some given interval ab. So in other words, the input to this problem is your integrand. All right, so you have some fixed interval ab, and you're given some function f, and your goal is compute this integral on this interval ab. Okay. So how we would understand the conditioning of this problem is the forward error. I should say the absolute forward error. So that would be the integral, and I'm going to use this notation, integral from a to b. So think of a as a subscript by the underscore, b as a superscript. So this is a definite integral from a to b, and this would be of f hat minus f, dt. So now keep in mind, we're treating the approximate solution as the exact solution of a nearby problem. This is your modified input now. This plays a role of your x hat. Okay. And then if it was a relative error, relative forward error, it would be the same thing, the integral of the difference of these two, divided by the integral of f itself, provided that it's non-zero. But if your exact value is 0, you cannot use relative error. So that's important to keep in mind. But here we'll assume it's non-zero. Okay. Now, what we'd like to do is get an idea as to how large this can be. Now, okay. I also need backward error. Okay. Now, backward error is a little trickier in this case. The absolute backward error, well, normally I think, okay, it's the difference of your inputs, your exact input, your approximate input. So f hat of t minus f of t. But here's the problem. These are functions, not numbers. We really want these measurements of error to be numbers. So what I'm going to do is I'm going to, by closing these in double vertical bars, that's a norm. A norm is a measure of magnitude. And the magnitude that I'll use in this case is the maximum of the absolute value of these two on AB. Okay, because that's the interval of interest here. So at least we can describe a backward error as a number. So, and then for relative backward error would be the maximum of this difference divided by the maximum value of f on AB. Okay. So now I can look at condition numbers. The absolute condition number, so that would be the absolute forward error, so the integral of the difference, divided by this difference right here between the two functions. Now, that by itself doesn't tell me very much, but I can simplify this quite a bit if I only care about estimating the condition number. I don't need to get it exactly. The exact value of a condition number generally means very little. What we really care about is ballpark. Is it small? Is it large? And that we can get for this by kind of an upper bound for this. So it's less than or equal to, because the integral, oh, hold on. I need to put, dang it. Sorry, I need to edit this a little bit. I need absolute value here. Okay. I should have put that up above, but condition number always works with absolute values. Okay, so it's the absolute value of this integral divided by this maximum value down below. Now, this is less than or equal to, the absolute value of an integral is less than or equal to the integral of the absolute value. So you can move the absolute value signs inside the integral as long as you replace it with less than or equal to. Okay. Now, this is less than or equal to this because this is, in the double vertical bars, that's the maximum difference. So this is less than or equal to the integral from a to b of the norm, in other words, the maximum value of difference on AB. Okay. Now, this is just a number. This is just since it's the maximum difference, it's no longer a function of t. It's a constant. So here we have the integral of a constant function. And this constant cancels with this constant down below. So it's less than or equal to the integral from a to b of 1 dt. That's just b minus a. So b minus a is the absolute condition number for this problem. Integration, which is one of the later problems we'll consider, is generally considered a well-conditioned problem. It's not quite as sensitive to errors, unlike its inverse problem, differentiation. That is much more sensitive. And we see this here that's not very sensitive in terms of this decent-sized condition number, especially if you have a reasonably small interval, like 0 to 1 or minus 1 to 1. On the other hand, if we take a look at relative condition number, so that would be, well, something that's going to get a bit messy. But we have, I'm going to define some shorthand here. If I use square brackets, I square bracket f, that is a shorthand, it's actually commonly used shorthand for the integral of f from a to b. Okay. So now I can say that the relative forward error, that's the integral of f hat minus f divided by the integral of f. So that's a much shorter expression. And relative backward error is the norm of a difference divided by the norm of the function. So now I can compute a condition number. So the relative condition number is just relative forward error divided by the relative backward error. So that would be absolute values around everything. Integral of a difference times the maximum value of f divided by integral of f times the maximum difference between the two. Okay. Now, this is a bit harder to decipher than the absolute condition number. However, there are certain circumstances under which this can be large. For example, what if the integral of f is small, the exact value, even though f itself is large. And when can that happen? For example, can be large if f is very oscillatory on AB. So if a function is very oscillatory, it's going above and below the x-axis. So you may have a function, even if it assumes large values, if the positive and negative areas cancel each other out, the integral of f can turn out to be very small, or maybe even near zero, and that can cause this to be large. So it's not always a nice problem, but as problems go, numerical integration is not so bad in terms of conditioning. So this is an example of how even a function can serve as input to a numerical algorithm for purpose of studying condition number, forward and backward error, etc. You just have to have an appropriate measure of magnitude. In this case, the maximum difference between the functions, or maximum value of a function on a given interval. Okay. So any questions about the error analysis in this case? Error propagation. That's what I mean by error propagation is, as you are performing a complex computation, and you may already be aware of certain uncertainty in your input. How is that uncertainty possibly magnified or damped as you perform more computations? So for example, if you take a function like, so suppose your x is pretty large, but maybe it has a small error to it. But you then substitute that in, say, an exponential, and that tiny error could now become something significant. Like, for example, what we do now to solve systems linear equations, Gaussian elimination, etc., when that was first being done by computers, people were actually convinced that it could not be done in any reliable way, because we knew about errors in computer arithmetic, and what if that error just compounded, was compounded by thousands of computations, so that the error in the overall result is still too large. And it took a very careful analysis done back in the 60s to prove, beyond a shadow of doubt, that, okay, whatever the errors in the input, here's how bad it can possibly get. So for example, if you have your input, like here's what you've measured, and you know it's within some interval, that could lead to intervals for your answers also. At least you get a ballpark. The trouble is that ballpark can get pretty large if you're solving an ill-conditioned problem. It's very easy to assume that if simply by using very accurate measurement devices, that anything you do with those results is also going to be just as accurate. And this is meant to dispel that. Other questions? Yes?
It's mostly that I don't understand why we use Y for forward error and X for backward error.
Well, just because forward error is about the error in the output, and backward error is about error in the input.
I guess why are we saying it's backward if it's for the input?
Probably because of I guess we're talking about how did it come to be called that. Yeah. I think the reasoning is that it's always been about understanding the size of a forward error, and let's say if I just simply refer to that as error, not giving any adjective to it, because that really is the goal. But maybe it's because they're understanding that error in the output by going backwards to look at error in the input. I guess it's that perspective of looking backwards that led to that thinking. Yeah. Yes. Between what? Between them directly, no, but it's just a matter of, are you interested in analyzing absolute error or relative error? And wherever you're interested in relative error, absolute error, that determines which condition number you should use. Okay. And generally, relative error is the one of interest. So the exception is if your exact values, where we're talking about the exact input or the exact output, are 0 or near 0, then you need to use absolute. Most cases, relative error gives you a better idea of how accurate your approximation is. In my research, for instance, I always use relative errors. Other questions? All right. Now, another thing that's brought up in this section is convergence. If you have a sequence of elements indexed by n, and n is going to infinity, and the sequence converges, how rapidly does it converge? Or if you have a function, f of h is going to 0, and how rapidly is it going to 0? This is a completely different viewpoint compared to other courses where convergence of any kind comes up, like for instance, convergence of sequences in series in Cal 3. The only concern in that setting was, does it converge at all? Here's a situation where if we've established that it converges, how rapidly does it converge? Because we know it's going to cut off at some point. We want as rapid convergence as we can get, because otherwise we're expending too much computational effort. Now, what I'm going to do to illustrate convergence is something that is be kind of a pain, even more than this, to type into MATLAB. So I'm going to try something different. Well, I'll indicate what. Okay. I'm going to prepare right in front of you now, and hopefully I can do this in time, a LaTeX document. The textbook, any notes, any documents I produce for my classes are done in LaTeX. That's for mathematical typesetting. Any real mathematicians use LaTeX, not Microsoft Word. And I don't care if that insults anybody, it's true. Now, this is software that I recommend. Actually, when I was a graduate student, during my first year, I switched to doing my homework in LaTeX instead of on paper. My grades shot right up. They could finally read what I was doing. So if you're on Windows, how you can LaTeX can be acquired for free. Go to mictech.org to download it, and then for a Mac, okay. So I don't remember the exact URL, but if you search for MacTech, I think it's at tug.org. But if you Google that, you'll find it. Okay. So if I switch to my editor, whoops. That's Text Shop. Right now I have a textbook open in it. So here's what I actually type in. And then this is a PDF that's produced. So what I'm going to do is I'm going to get rid of this. Okay. And create a new document. Okay. And I have to unfortunately type in. And if I go through this too fast, keep in mind this is being recorded. You can watch the video later. So I'm just creating a bare bones document. I'm specifying it's an article. Oh, actually, I'm going to put something else in the diary here for you. I gave a LaTeX workshop some time ago for a SciAm chapter. So if you go to this web address for a SciAm chapter website, which I need to update. So if you go there, you get some samples, like for instance, for like what I'd use for lecture notes, or a resume, or a presentation, or a thesis, things like that. There's several samples there that you can look at. Okay, but I'm going to illustrate some things in here. So what I'm going to do is I'm going to create an array of equations because I want them to be lined up. Okay, and I could type in ordinary text, but if I use $, that puts me into math mode. So I want to talk about approximation of a second derivative of a function at a given point, x naught. Underscores are again subscripts. And I'm going to use a Taylor expansion around x naught. Okay, so as I type this out, I'm going to periodically generate a PDF so you can see my progress. What I'm typing here, you definitely don't want to bother writing down. The ampersands are used to help this line up. So I'm going to type out the Taylor expansion. For f of x naught plus h, expanding around h. And here I'd normally have x minus x naught, but that's x naught plus h minus x naught, but that's just h. And then I can use frac to do a fraction. Notice backslashes are used to indicate this is a LaTeX command. So backslash frac means do a fraction. The first item in braces is a numerator, second item in braces is a denominator. And I want f double prime x naught, and I'll keep going, 1, 6, triple prime, and I'll go to one term more, and I have f. I'm going to use this notation for fourth derivative because 4 primes is kind of hard to read. And at the last term, this is my last term, it's not x naught, it's an unknown point. I'm going to call it xc1. Xc is a squiggly Greek letter. In fact, in class I've often called it squiggly. H to the fourth. Sorry for getting my powers of h here. Okay, and double backslash ends the line. Now I need to save this. Okay, I'll put it with my other Math 460 documents. And I'll post this on the examples page of the site later. Okay, so this is my second derivative approximation I'm talking about. Okay, so, and what it'll save it as, actually I should make sure that I did that properly. Ah, dang it. Okay. It's supposed to put a .tex extension. It'll be fine for now. Oh, okay. Yeah, put it there anyway. All right, so if I do typeset, it'll generate a PDF. Thankfully, I had no errors. And I'll magnify this. So here we have my Taylor expansion. It's a good idea when learning this to see, here's your output, here's what I typed in. You can see how one corresponds to the other to learn how to generate certain expressions. And now I want to do the same thing with f of x naught minus h. So I just need to change my pluses, replace h by minus h throughout. But minus h quantity squared is the same as h squared, so this term stays the same. So terms of odd powers of h that change. And my unknown point will be xc2. Okay, and being able to copy, paste, and change things certainly makes it easier to produce these documents quickly and legibly. And where xc1 is in, so this backslash in is for inclusion, the stating an item as an element of a set. So it's between x naught and x naught plus h. And xc2 is in x naught minus h and x naught, just to be precise here. Okay, so actually, I don't like having that much space, but that's because I put this in here, which I should not have. You don't need it for the last line. So now what I'm going to do is I'm going to add these together, and I'm also going to, and the thing is, when I add this, I'm going to get 2 f of x naught. These terms will cancel, the f prime terms. The f triple prime terms will also cancel. These won't, and these won't. These won't either. But I do want to get rid of this. So I can say, so if I add these, I get, okay, so f x naught plus h minus 2 f of x naught plus f of x naught minus h. So what will happen is then all the f of x naught terms will cancel out. These will cancel out. So what I'll get is, and then these two will add together. So I'll get f double prime of x naught times h squared. These terms cancel. These will add together, but I can't really simplify. Well, I could kind of simplify them, but 1/24th, and I'll have h to the 4th times, and I'm going to be lazy and copy and paste these. That part plus that part. Okay. So now I have, so this is what I get from combining these expansions. I get what I want. I want the second derivative, except it's times h squared. So now I'll just go ahead and divide both sides by h squared. And I'll just copy and paste this and fix it. I'll put this as a fraction. This will be the numerator. And then I'll put h squared in the denominator. And then I'll take out a h squared and everything else. Okay. Okay. Now, I'm going to manipulate this a little bit. So in fact, I'm going to make this another equation array. I want these to line up. So I'm going to get rid of the double dollar signs. A single dollar sign puts math in line text. But a double dollar sign, like I have here, makes it a displayed equation. So you want that for large or tall equations. Now, but for lining them up, I have an equation array. Okay. Now, so now I have that. So, stop it. What I want to do is, I want to keep messing with this right side. I want to leave the left side alone. So on the left side of this, I'm not going to have anything. I'll have my modified right side over here. Whoops, I made a mistake. Oh. I mistyped equation array in the end here. So. Oh, also, if I want to give this document like a proper title, I can specify the title. Convergence of what's called a center difference for second derivative. You have an exploration, and this is homework 2, about the first derivative. So I was doing a slightly different example, derivative, and then I'll put in the author. And then if I say as soon as I begin my document, make title, then it'll put all that in there, and also put in the date of today's date. Okay, so now I want to mess with this. I'm going to divide up the 1/24 factor. So it'll be 1/12, and then I'm going to put a 1/2 over with these terms here. And the reason for that is what I have here is the average of these two values of a fourth derivative at these unknown points xc1 and xc2. And what I can do is I can replace that with, instead of the average of two function values, I can replace it with a single function value. Okay, and the reason I'm allowed to do that is if we assume that the fourth derivative is continuous, and I'll fill in all these pesky assumptions in here, for which any one of my colleagues would mark off points on me, by the intermediate value theorem, this function somewhere between xc1 and xc2 is equal to the average of these values. So that continuity in the intermediate value theorem lets me condense this. So now what I can say is, if I just rearrange this, is that the second derivative at x0 is equal to my approximation, which I'll just paste from over here, minus this expression. I have to move it, so I'm moving it to the other side. I want the exact value by itself. Okay. And what we have here is, here's my exact value, this is my approximation, this is my error. The error is proportional to h squared. So, so the conclusion here is that the error is big O of h squared, because what we can say is that this error, the absolute value of this error term is less than or equal to h squared times some constant, which would be an upper bound on the magnitude of the fourth derivative. So that's because big O notation is about upper bounds. A lot of what goes on in this chapter is finding upper bounds for functions. Basically, you can replace a function by a simpler one that you know is bigger than it. What I could say here is, if I take the error term, okay, I know I'm running out of time, and I'm going to put absolute value, but this is a tall expression. If I just put this in vertical bars, that looks pretty tacky. So what I'm going to do is I'm going to make these vertical bars bigger. I'm going to put backslash left in front of a left one and backslash right in front of a right one. What that does is it sizes these delimiters based on the height of the expression in between. So it makes it look more professional. And it drives me nuts when I review people's papers and they forget to do this. So this is less than or equal to h squared times 1/12 times m, where m is a bound on the fourth derivative on this interval, x0 minus h, x0 plus h. And the reason I can say that is x1 is between x0 and x0 plus h. x2 is between these two values. xc is between x1 and x2. So this value xc is between x0 minus h and x0 plus h. So as long as I know how big the fourth derivative can possibly get on this interval, I can say that this error term is less than or equal to big M over 12 times h squared. Therefore, by the definition of big O notation, I can say that the error is order h squared. So what does that mean? That means that as you decrease h by a factor of 10, let's say, then the error will decrease by a factor of 10 squared, or 100. So we like to have higher powers of h in our error formulas, where h is going to 0. That means faster convergence. So we're always trying to develop methods that will converge to our exact values more rapidly. We're going to see this with derivatives and integrals later on. When we are trying to find roots of equations, we want to we go to great lengths to try to speed up convergence of our approximate values to the exact values. So in one of the later explorations, last one's in section 2.1, you're doing this exact same thing, but with the first derivative. So if I show you this example, that's kind of like that. Just to get an idea of how you come up with these error formulas and how you because what you're going to see is two different orders of convergence. And if you try out these formulas, you see a big difference in how accurate they are. So for example, if I look at okay, I know I have 1 minute. I'm going to let f of x be equal to, I'll just say sine x. X is equal to 0, and h is equal to 0.1. So f double prime of x is minus sine. So f double prime of 0 is equal to 0. So if I look at h equal to 0.1, and I'll do sine of, okay, and x naught will be 0. So sine, someone tells me I'm going to regret this, but we'll see. Oh, I shouldn't have picked that one. I get some symmetry and cancels things out. I'm going to choose a different x naught. 0. Let's say pi over 4, let's say. Okay. So now the exact value is minus sine of x naught, which is minus square root of 2 over 2. Okay, so if I do that, okay, versus the exact value, it's not bad. We have first 2 decimal places correct, third decimal place almost correct. If I do h to be 0.01 and I do the same thing, then we see that we have 1, 2, 3, 4, 5 decimal places correct. So we gained quite a bit of accuracy in that case. And if I were to keep going, then we see comparing this value to this value, we keep gaining a couple extra decimal places each time. Whereas if I use like a first order accurate method, we wouldn't see nearly as much improvement. Okay, I know I've gone 1 minute past time. So, so be sure to take a look at this section again, and keep in mind on Thursday we'll be looking at computer arithmetic. We're going to get a little computer sciencey on you, unfortunately, and go from there. And get homework 1 in. Dang it.